Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today as it is every day here in my virtual classroom. Step on inside, we are going to be looking at section 5.3 in the Big Ideas Math Integrated Math 2 textbook on two-way tables and probability, as the whole chapter is actually literally on probability. I think we actually got a sneak preview on two-way tables in a previous problem, and I wasn't actually sure how to solve, I know how to solve the problem, but I wasn't sure how to present it, because I was like, you haven't learned two-way tables yet, so am I supposed to teach it and talk about it? And I sort of did. There were two problems actually on it now that I remember, because I showed the totals, and I believe that this is where we show those totals of these values in these two-way tables. You'll see the visual of what it looks like, and if we have to create some for ourselves, I might have to come up with a template and then copy and paste it as well. So there's some time that may be built in some of these things, and as always, grab your calculator. We have to do some sums with these. This is one of those ones where I like to do things more in my head if I can, because I'm lazy to just click buttons on a calculator. So I apologize if I get anything wrong when I go over the problem set and the solution guide things. I should always double check my work, and you should always, of course, double check your work. This solution guide video is just a boy in his bedroom, you know, just making videos, and I want to make sure that you are following along with your stuff and you're learning along the way. But if I say 2 plus 2 is 5, you got to correct that yourself, if that makes sense. Anyway, I keep saying I hope that these videos are going to be shorter than the other ones. I hope that this one is as well. Although you live within a problem for a little while, coming up with some values, maybe we have to interpret them. So let's hope the lecture part is actually shorter, because the last ones were about 20 minutes long each. This intro was not shorter, however, and if you want to check the description section down below and find a specific place that you want to look for, we're going to start with the lecture portion and then go to the problem set. You can go ahead and find those timestamps with that, as well as download the PDF of what I'm going to be doing right now. So, guys, sit back, relax, and enjoy your flight as we move into section 5.3. We're going to learn to make two-way tables, so I guess we're going to do some ourselves. Find relative and conditional relative frequencies and conditional relative frequencies, and use conditional relative frequencies to find conditional probabilities. It's okay if you don't know what those things are. They're going to be teaching them to you, but we've seen the word conditional before. In fact, they show conditional probability as this thing, and a bunch of different phrases. And I'll be honest, I always confuse which ones are which when they talk about joint versus marginal. I shouldn't. And I mean, I shouldn't, not just because I shouldn't remember. I should just see the word and say, I understand it. But if someone asks me, off the top of my head, 2 years after doing anything with stats, what is a joint frequency? And I'll say I can't remember which one. That's okay. As we talk about it here in a vacuum, I'll be totally fine with it, and I hope that you are as well, at least with doing the two-way tables. All right, guys, let's go ahead and see how we make two-way tables. First of all, let me show you the visual as I read this. This is an example of a two-way table, and it can expand more than this, not just with categories, but with totals. A two-way table is a frequency table that displays data collected from one source that belongs to two different categories. One category of data is represented by rows, and the other is represented by columns. So whether you're a freshman or sophomore class, or attending or not attending something. Suppose you randomly survey freshmen and sophomores about whether they are attending a school concert. A two-way table is one way to organize your results. So, and I'll just go this place as well. Each entry in the table is called a joint frequency. So I said joint versus marginal. These are the joint frequencies right here. These are the values represented by something, and I think you can interpret it for yourself, but let's take a look. The sums of the rows and columns are called marginal frequencies, which you'll find in example 1. So you don't see them just yet, but you're going to see totals of these things like 25 plus 80, things like that. But the joint frequencies, here's this breakdown that we're looking at here, right? How many freshmen are attending the concert? 25. How many freshmen are not attending? 44. So within this row, you see all the freshmen who are attending versus not attending. This is where the conditional aspect will come into play. How many freshmen are attending versus not? That excludes sophomores, you know, but how many sophomores attend? How many sophomores don't attend? How many attending are freshmen? How many attending are sophomores? How many not attending are freshmen? How many not attending are sophomores? Like that. And that's the way that we can read those values. And of course, totals, marginal frequencies, it sounds like they'll show up right here. Are these different junior? Yeah, these are different questions coming up. Example 1, making a two-way table. In another survey similar to the one above, you have 106 juniors and 114 seniors who respond to the survey. Of those, 42 juniors and 77 seniors plan on attending. Organize these results in a two-way table, then find and interpret the marginal frequencies. So here's the interesting part about this, and I need to kind of work this out in a way that's helpful to what, because this is already pre-filled out, but let me, what do they say? 42 juniors, 77 seniors. So this number's, the number's not yet known, technically, are these numbers here and these numbers here. And I'll hide them in white, even though that's gray. So this is all they told you, really. They said 106 juniors respond. Boom, 106 juniors. So here you have the juniors, and the total's 106. By the way, here are the new parts of the two-way table, the marginal frequencies, as the joint frequencies are added together to get those. So we know how many are attending. How many are not attending? They're saying that you subtract 42 from 106 to get 64, and that's where this number comes from. So we're going to be doing these same kinds of things. We're going to be doing addition of and subtraction of to find values. Same thing, 114 minus 77 can get us 37 seniors that are not attending. So I can go ahead and remove that one as well. That's where we come up with them. After that, you get these totals. 42 plus 77 is 119. 64 plus 37 is 101. And of course, you have the total, which is nice to look at here. I'm sure that they say this. Yes. Find the sums of the marginal frequencies. Notice the sums 106 plus 114 is 220, and 109 plus 101 is also 220. If they don't add up to the same number, which is one of my double checks I'll do, if they don't add up to the same number, something went wrong. So here, clearly something went right, and I think they just said, fill this thing out and you're good to go. But notice how we're creating totals if they were not made for us. There's a lot of information you can come up with. Joint frequencies here, marginal frequencies here, and the total here. Okay, let's move forward. Finding relative and conditional relative frequencies. You can display values in a two-way table as frequency counts or as relative frequencies. Now we're talking about like probabilities. So I'll show you this here before you just keep hearing the phrase joint relative frequency and say, what are you talking about? You're dividing something out of a whole, and in this case, it's the same example thing as before. 220 is that whole amount. Okay, now we'll talk about how those sums work out in just a moment here. A joint relative frequency is the ratio of a frequency that is not in the total row or the total column. So these are joint relative frequencies, just like I think the word was joint frequencies that we were talking about before of the 42, 77, 64, and 220. But now you divide by 220, you divide by the total. A marginal relative frequency is the sum of the joint relative frequencies in a row or a column. So the sum of these ones, boom and boom. Now don't round early because do not use rounded values to come up with the total. Use the exact ones whenever you can. So do this plus this instead, because both of these could be rounded. For example, this plus this, maybe two rounded values. But this plus this is that, 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 this plus this is that. And notice that the total here is 1. 1 is the 100% of everything that's included. 220 divided by 220. So these should always add up exactly to that amount. If not, something went wrong. Keep in mind, these are rounded values potentially. So the rounded values may not add up to 1, but the exact ones should. So listen, I just said everything for this example that we needed. We're dividing by 220 in that scenario. So I'll just kind of move on from that. Now, there are things called conditional relative frequencies. I don't know if I said that one yet. A conditional relative frequency is the ratio of a joint relative frequency to the marginal relative frequency. You can find conditional relative frequency using a row total or column total of a two-way table. We've talked about conditional things before, and I want to bring this up again. Use the marginal relative frequency of each row to calculate the conditional relative frequencies. And you can find conditionally how juniors and seniors compare to attending and not attending in this way. The 0.482 number is what's being divided here. Now, we've done conditional probability. In conditional probability, we're not dividing by the entire amount that is 1. Instead, we're dividing by 0.482, 0.482 being the total represented here. Now, I would probably tend to use the actual numbers themselves, meaning, I forget what this number was. Let's say it was 114. I forget. That we divide, that 114 divided by 220 is this number. I'd probably use those ones here, but 0.482 is the total number of juniors, the probability that you're looking at a junior, the spread of juniors in the statistics. So we're looking at how many juniors overall, given that you're a junior, are you attending or not? So 39.6% of all juniors are attending. 60.4% of all juniors are attending. Whereas before we were looking at just this 19.1%, that's 19.1% of all upperclassmen, of all juniors and seniors. But here we're not counting the seniors. Here we're just counting juniors. And here we're just counting seniors. So these total will add to 1 on their own. These total will add to 1 on their own. So they're telling you here 32.4% of all seniors are not attending. So this is conditional with respect to juniors and seniors, not attending and not attending, but the juniors and senior classes there. They could do a separate one for those, and it doesn't look like they're showing you that one. They probably ask about it here, but I'm not going to do it right now. Finding conditional probabilities. You can use conditional relative frequencies to find conditional probabilities. This is probably what I was referring to before, and this is what I'll be doing. A satellite TV provider surveys customers in 3 cities. The survey asks whether they'd recommend the TV provider to a friend. The results given as joint relative frequencies are shown in the two-way table. So this is already the percentages that would add up to 1, like 29% of responders responded yes and they are from Glendale. 5% responded no and are from Glendale, things like that. So this adds to 100%. What's the probability that a randomly selected customer who is located in Glendale will recommend the provider? Notice they said who is located in Glendale. That means we are looking only specifically to the Glendale crowd. So in the Glendale crowd, we're only looking at this total here, the 29% and the 5%. We're only looking within that 34%. And within that 34%, there is a chunk of 29% of the whole that did respond yes. I think that's what they asked, right? Random selected. Will recommend. So recommend yes. So we're going to divide 0.29 by 0.34. 0.34 being the sum of 0.29 plus 0.25. The 29% out of 34% that we're looking at. So 85.3%. I'll read their sentence. The probability customer who is located in Glendale will recommend the provider is about 85.3%. And again, you might say, no, Mr. Robinson, it says 29% of people are from Glendale. And that's not what we said. We didn't say 29% of responders. We're talking about the percentage of Glendale responders. So just within there. That's what makes this conditional. Part B, what's the probability a randomly selected customer who will not recommend the provider is located in Long Beach? By the way, conditional probability, they could also say given that they did not recommend it. So we're looking at the no crowd. And among the no crowd, if you add that result, 5% plus 3% plus 4% is 12%. So among that 12%, 4%, not 4% of the 12%, but 4% out of 12% are in Long Beach, and that's a third of all of them, so 33.3% there. So there's that division by taking the total of all the no's. Again, this is conditional probability stuff, Long Beach, given that there are no. And then the last one, determine whether recommending the provider to a friend and living in Long Beach are independent events. Well, we've seen that from independent dependent from section 5.2. So what we have, recommending the provider to a friend. So here's recommending to a friend, okay? And now that total would be 0.29 plus 0.27 plus 0.32. And that's shown, I'm trying to scroll down. That's this one right here. That's this total. Remember, that's not necessarily one. And then, and living in Long Beach. Provided to a friend and living in Long Beach are independent events. So now you got to see all the yeses that live in Long Beach as well. So that's 0.32 out of that one right here. Now, when you look at the probability of all those who live in Long Beach, that's 0.32 plus 0.04. So all the Long Beach mates are 0.36, 36%. And then this one is also 36% when rounded. So I think the intention is that they want those to look the same. So yes, because the probability of living in living in Long Beach? Probability of Long Beach responders. Yes, living in Long Beach. Probability of living in Long Beach is about equal to probability of living in Long Beach, given that you are a yes voter, then they're independent events. We'll have to dive more into those ones because what I always want to come up with, which I'm bad at, is interpreting what this actually means instead of using the formula. But the formula is showing that the probability of B is equal to the probability of B given A, that they need to be the same thing here. Okay, so I'll make sure to hopefully clarify that better because I kind of followed the example more than I was thinking for myself in that last one. Example 5, comparing conditional probabilities. Already 14 minutes in. Hopefully this is the last page of the thing. A jogger wants to burn a certain number of calories during his workout. He maps out 3 possible jogging routes. Before each workout, he randomly selects a route, then determines the number of calories he burns and whether he reaches his goal. The table shows his finding which route should he use. So route A, he reached his goal 11 times, didn't reach it 6. Route B, he reached it 11, didn't reach it 4 times. Route C reached it 12 and didn't reach it 6. So, those are numbers, right? That's 11, 6, 11, 4, 12, 6. And you can kind of use those to come up with things that you divide out of the totals. The total is, they didn't write the numbers in between here. They just show the tally marks. And let me move myself actually now. But they divided these, right? Whatever 11 plus 12, that's 34. Plus 6, 40, 44, 50. So these add up to 50. If I divide 11 by 50, I get 22%. So they have 0.22. So you see the numbers here. They kind of divide them into numbers there. And it's important to see things in a relative sense, relatively. Because sure, that's great that this is, 12, whatever, what have you. But when you compare that 24% to, like, say, this 12% here, it's going to show you a different kind of picture that we're talking about. Okay, we make a two-way table, shows the relative frequencies. There are 50 observations, so we divide them by 50. Find the conditional probabilities by dividing each joint relative frequency by the reaches goal column. So, because the question says what route should he use? The route that you'd want to use is the one that gets you the best probability of reaching your goal. So what they're doing is they're looking at, hold on, or did they say it the other way? Yeah, which route gives you the best chance of reaching your goal? Probability you reach your goal, provided that you ran in route A, is 0.22 out of 0.34. You have a 64.7% chance of reaching your goal if you run route A, and then 73.3% chance of reaching your goal if you run route B, 66.7% if you run route C. Didn't matter that route C reached his goal more times, even though it was one more. Didn't matter that you reached it more times than route B. The fact of the matter is this was a better, higher success rate, because this is 12 out of 18 and this is 11 out of 15, right? That's what those numbers are based off of. Now, they tend to use those numbers there. I probably, once again, want to use these ones as a whole, just because I don't like dividing decimals by decimals unless I have to. So there's that answer. There's that work. Okay, guys, we are done with the notes portion. So it was shorter, not by very much, but let's go ahead and dive into these, see what's going on. The vocabulary and core concept check. Let's complete the sentence. A blank displays data collected from the same source that belongs to two different categories. How soon we forget, it is known as a two-way table. All right, compare the definitions of joint relative frequency, marginal relative frequency, and conditional relative frequency. Well, they're all relative frequencies, so that's great. But the joint relative frequency compares, displays percentages, or decimals, but percentages of the joint marginal, the joint frequency values out of the total number of, I'll say out of the total number, because I don't know if it's always voted people or whatever the survey responders and all that stuff. Whereas the marginal relative frequency displays the sums of those joint relative frequencies in the rows and column for each row and column. And again, you can come up with those. You don't have to do the addition of the joint relative frequencies to get those values. You could also, of course, do the division yourself, dividing the marginal frequencies by the total. Now, the conditional relative frequency compares or divides joint relative frequencies by marginal relative frequencies instead of totals. Instead of the total, the total, because you're only comparing within a certain row or column. So I'm only typing as much as I can kind of fit within there. So there it is. All right, guys. And that had to do it for the lecture portion and for the vocabulary and core concept check. Now we are going to go ahead and dive into the actual problem set, for which we have, you can see it before I can, 26 problems. We've had small numbers before, but they still seem to amount to near 2 hours when we're doing them. So let's go ahead and get started and see what it's going to look like. Excuse me. In exercises 3 and 4, complete the two-way table. So it's best that I really do a copy and paste. I'll leave the blank one on that side because I'm going to write on this side over here. But number 3, we're going to do that. All right, complete the two-way table, guys. It's all about the totals. I could interpret this stuff as well if you really need me to, but we're looking at what grade, if students pass or fail, I guess students, if students pass or fail something and whether they studied or did not study. Now, what we have to do is kind of work through this the best way we can as far as find totals where we can. Something plus 10 equals 50, and that number would be 40. And because of that, now I can find out how many studied based on the number who didn't study in the total. If 6 didn't study out of 40, then 34, that's a subtraction, right? 34 out of 40 did study. And now with that 34, I can gain that 4 people failed among those who studied. And so there's that. Now, how do I find totals here? You got things within. I can do 10 minus 4 to get 6. I can do 50 minus 38 to get 12. I could have also done 6 plus 6, which is 12. Everything here should combine the right way. So this plus this is that, this plus this is that, this plus this is that, and so on and so forth. It seems to work out. Two-way tables completed. Now, it just goes to show that you should study because you're more likely to pass. Only 50% of people who didn't study did pass, whereas much closer to about, 85 or so percent of people who did study passed. So, hey, study. All right, number 4. Let's do the same thing. And I don't really have much to say on this stuff. It's just strategically, you have to have 2 of the 3 values somewhere before you can end up filling it out. And then once you fill one part out, it helps fill out other parts. So like, I can't fill this part out yet based on this column, but once I find one of the parts, then I can. And actually, I can based on this row. 3 plus 7 would give you 10. What is this? Whether you're a student or teacher, respond yes or no. So those aren't necessarily like correlated. Like, I feel like because you studied, you're more likely to pass. But the yes or no part here, I don't know. It depends on what the question is. And 42 plus 7 is 49. Obviously, it's a subtraction. If I add these 2 numbers here, I'm going to get 98. And 98 plus 10 is 108. So my expectation here is when I add these 2, that adding these 2 should also get me 108. 56 plus 3 is 59. And 59 plus 49 is indeed 108. So you want to just definitely double check everything there. All right, cool. Let's move on. Let's go to number 5. You survey 171 males and 180 females at the Grand Central Station in New York City. Of course, of course, of those, 132 males and 151 females wash their hands. Oh, why would you volunteer that you don't wash your hands though? Wash their hands after using the public restrooms. Come on, wash your hands. That's icky. I gotta provide my own commentary. That's gross. It's good that they did, but listen, I'm going to come up with the number right now. 39 didn't. 39 males didn't. 39 females didn't. 29. I'm already coming up with the number. Organize these results in a two-way table, then find and interpret the marginal frequencies. This is where I said I'd really love to have a template thing already pre-made. And so, you know what I could do actually? The thickness might not work right. What is this? 2 with a total and 2 with a total. I can spit this out right here. I'm making a 3x3. Oh, shoot. Oh, wait. Actually, I need the categories with the total. Okay, I need to make a 4x4. So I'm going to make kind of a 4x4 table, and I can shrink it, and maybe I can just use this idea and, fill that one out each time. Hopefully this is big enough for what I'm doing, especially since I kind of write, sideways as we do as humans. So hopefully this works out the way we want it to. Now this space won't have anything. It's one of those, this space is intentionally left blank kinds of things. Let me actually whiten it out instead. There we go. And yeah, we can fill this thing out. Let me keep working on it. Can I gray? Oh, cool. Hold on. These are totals, right? So total. Can I select multiple? I guess not. Fill colors. Give me 1 second. I want to just play with this for a second. Aha. That's a little dark, but that's okay. I'll make it dark. So let me pause and make these gray for a second. Hold on. All right, so I did you one better here. I tried to color things, not exactly like these, but I tried to make the coloring things look like they were before. So I'll try and copy and paste this, like I can use it again in the future. Let's see. Cool. Use it again in the future. Problem is, this is only for 2x2 kinds of things. So the bottom ones are totals. I should probably write that as well and make sure that that's kind of within. Total and total. The only thing I don't have are the actual categories by name, just how they're separated. So like there's one set that'll be gender. So I can do like male and female. And then it's about washing your hands versus not. Wash hands and no wash hands. There's actually have Planet of the Apes in the background here. So Caesar, no wash hands. Yeah, let's see. You survey 171 males and 180 females. So those are the totals. A total of 171 and a total of 180. So that's a grand total if we want to work that out early. It just says fill this out. So 351. Yep, 351 is a total. Now they said that 132 males wash their hands, 151 females wash their hands. Not only can we get that total here as well, which is 283, not enough. There it is. So organize these, find and interpret the marginal frequencies. Yeah, let's keep going. I said this number was 39. That's the subtraction of this minus this. And 180 minus 151 is 29. 39 plus 29 is 68. So they said find and interpret the marginal frequencies. Those are the ones inside the totals. And I actually probably could have typed with in there. I'll test that out next time because I'm going to test this one out or type this one out now. 283 total responders. Yeah, because people, right? It's all male and females. Wash their hands and 68 do not. Not 86. That's way too many. 68 do not. That's too many who do not. And then there are 351 people total. And that's my interpretation, at least for now. All right, there's number 5. Let's go ahead and take a look at number 6. A survey asks 60 teachers and 48 parents whether school uniforms reduce distractions in school. I never knew that was actually a topic of conversation. Now that I realize that actually probably would be a big topic of conversation. Of those, let's see. Actually, let's talk about the categories here. Can I type in here? I can, but will it look good? Let's see. Teachers versus, that seems too clean, versus parents and distraction. This is uniforms. So that'd be the category, right? Not distraction. I'll just not distract. Ooh, what happened here? No distraction. Okay. So I'm just kind of making what I want to get. So what do we have? 60 teachers. 60. I feel like I have to center all these. I'll write these in. 60. I'll do writing from here on out. 60 teachers and 48 parents is a total of 108 individuals. 49 teachers and 18 parents say uniforms reduce distractions. So not a distraction for uniforms is this one. Oh, let's see. Reduce distraction. I'm going to write them. Sorry about this, y'all. All right, reduce distraction. No, reduce distraction. Caesar. Ape together strong. Okay. 49 teachers and 18 parents say they reduce distraction. That's a total of 67. I'm kind of coming up with things as we can get them. And get the rest. That means 11 do not say it doesn't reduce distraction. And 30 parents. So teachers and parents are on way opposite ends of what we'd say with regard to that. Now it's 41 total. And they do say find and interpret the marginal frequencies. So we already have the totals of those ones here. So we're really talking about these ones. So 67 responders. Hold on. Let's do that again. 67 responders stated uniforms reduce distraction, whereas 41 say they do not. Yeah, there are more things that we could say with that when it comes to like the parents and such and such. Parents don't believe it doesn't reduce it and all that. And teachers, interestingly enough, I'd say with a poll, I would have figured it would have gone the other way. That teachers would be the complainers in in the ordeal. Okay, in exercises 7 and 8, use the two-way table to create a two-way table. Use the two-way table to create a two-way table that shows the joint and marginal relative frequencies. So now we're going to talk about relative frequencies. For us, y'all, it's going to be now a division of things by the total. So as a whole, I'll write them as fractions to begin with, and then we'll do the rounding. So we do have female and male as gender portions here. And then dominant hand is left and right. Okay, so the females, there are 11 left-handed females out of 231 total folks. I'm going to do the divisions after. There are one, and I'm not going to plan on reducing these fractions unless there seems to be a need to, but we're dividing everything by 231. Now, you could, for the marginal parts, either do the division. Hold on, 231. You can either do the division of, say, 35 over 231, or you can add the results of what you do here. And it's kind of an either or case. It's up to you. Whichever one you'd say is faster. For this one, I'll do this one this way, and number 8, we'll do the totals. How about that? 115 out of 231. That's gonna be about 50%, right? We can already kind of see that because this is kind of split down the middle. So without knowing a little more. And this is going to be 231 out of 231, right? So 231 and 231 we know is 1. There's nothing else I have to do with that. I think they did 3 decimal places for these ones. Well, actually, I don't know. I'll do 2 when it comes to like time and stuff that I have with it. So I'm just going to go to my calculator. I'll show you for a couple of them. We'll do 11 out of 231. Let's see if I can type faster than 24 out of 231. 35 out of 231. I didn't realize that I could be doing this typing all this time. Let's get those 3 first, and I'm going to go ahead and write those ones down. So I got point... How many decimal... Did it say? I don't think it did. Let me quickly check. Give me a second. I'm going to check and see how many decimal places they did use in previous examples. They used 3. They used 3 when they could. So I'm going to use 3 decimal places. Okay, so... I got to find where I was. Okay, so 11 out of 231, I'll say 0.048. And then 24 out of 231, 0.104. Now notice, both of those rounded up. That's a reason I don't want to use the rounded values when it comes to adding. And this is 0.152. Also rounded, it seems. It seems to round in the same way. So those are just the first 3 that I wrote down like that. And I'll continue to do the same off screen as I write them down. So we'll do 104 over 231, 92 over 231, and 196 over 231. Okay, so I have for this first one 0.450. I'll just write the 0 for precision purposes. The next one is 0.398. A lot more righties than lefties, right? And then total 0.848. The last ones I have there, oh, my mouse is stuck under my keyboard now that I was typing this. Last one's 115. This is going to be about 50% each. 231 and 116 out of 231. So 0.498 here. And here is 0.502. Now, these should also have the sums work out. So this plus this should give you that, it looks to be, and that, and that, and same thing this way. And they do look to be exactly that. I do wonder if there are times where there's an early rounding kind of thing that will not make them look the exact same. They might. We'll see if that shows up, but that is number 7. Okay, number 8. Let's do a copy paste job again. This one has, I'll just do this. I'm going to copy and paste the actual thing that's there because notice this is now like a 3x2 or whatever. So I don't have that one already created for that little table thing that I made, but I'm going to erase all the things that are here, right? Because I have to kind of make my own. So we'll do what we can. Experience and gender are used here. So the categories are the same. I just got to kind of get rid of these guys. So if it's okay with you, this time I won't write the fractions. I'll just do the division. And then when it comes to the totals, let's see if I can make the gray color same-ish. It doesn't look like it's exactly the same, but that's actually pretty close. If it's indistinguishable for you, then that's good. Cool. I can see the difference. That's okay. It's close. Anyway, I'll probably just do the division on the calculator, and I'll tell you what those numbers are. But remember, for the totals, I am going to add up the decimal bits. They will be early rounding, I suppose. I say not to round early. Maybe I shouldn't do that then. I don't know. Anyway, I'm going to start with 62 divided by 410. Keep in mind what you're doing the division for. So this male one is about, and everything's approximated, 151. Again, 15.1%. 275 divided by, I forgot, I should be typing these. Divided by 410 and 40 divided by 410. So this is 0.671 rounded, and this is 0.098 rounded. Let me show you the calculator. So with the total, you could add those three up. Just keep in mind, those are rounded values. So I'm going to test and see if I get the same value this time. You might not. 0.671. Remember, if you're off, you're going to be off by 1/1000th. But that matters for the total in the end. So those add up to 0.92 kind of in an exact way. I don't know if this other version would. It actually might, because their total is dividing by that 410. And they probably made it purposeful so that these would add to exactly that. So even though that was early rounding, maybe that was fully intentional. So what's the difference between that and 62 plus 275 plus 40? And all of those divided by 410? Whoops, 410. So see, that's the exact. That's as approximate as you can get, and then it still rounds to 0.92. So who knows? Maybe they made these with the intention of making sure that they still round to the same value, and if they do, then I'll just go ahead and trust that so we can move faster. So now I got to divide 6 by 410. 24 divided by 410, and 3 divided by 410 for the next three on females. There are a lot less females that were right here. And 6 over 410 is 1.46%. Oh, that's one too many things. 1.5%. That's a tenth the size of the males. Oh, 6 to 62. Basically, less than a tenth as an overall. 0.059. And this last one is 0.007. Less than 1% of ones who voted or responded were females, novice females. Anyway, let's add those three. What's 0.071? No, 0.081. See, I should leave it up to the calculator to do that. And that makes sense here. Remember, this is 0.920, but listen, here's an example of rounding error. This maybe shouldn't say 0.081. Let's actually go back, because here's the thing. 15, just look at these numbers. 15 plus 59 is 74. 74 plus 7 is 81. So that's where that 0.081 comes in. But this would add up to 1.001. They're supposed to add up to 1. So what I should be doing when I'm doing this, 6 plus 24 plus 3 is 33, right? What's 33 divided by 410? Well, that rounds to 0.0. It rounds to this. It rounds to 0.0804. So that actually rounds to 0.080. That is an example of not rounding early. So I guess I did make my point and I spoke too soon before. That should say 0.080. So y'all, don't round early. I don't recommend that you add these ones up. I didn't before anyway, but I recommend you come up with the total and then divide by 410. That's why I'm also not going to do it here. Let's just add the totals. What's 62 plus 6? That's 6. Oh, they already have the totals. 68 divided by 410 and 299 divided by 410. Because I feel like the book was preaching and asking you to add them instead of doing the division. Anyway, so these last numbers here, I'm speaking too long on this. 0.166, 0.729, and 0.105. This one would add up to 1, it looks like, but the other one would not. Okay, that was number 8. I didn't write that here. Okay. Let's go to number 9, modeling with mathematics. Use the survey results from exercise 5 to make a two-way table that shows the joint and marginal relative frequencies. So we got to go again. Where's number 5? Oh, it's one that we kind of made. So I guess I got to use it. Oh. Then let's... Hold on. Give me a second. If I copy and paste all this, does that take all the stuff with it? Yeah, good. All right, now I need to kind of do this twice because I need to see the numbers and then I need to change the numbers. So I need to change these ones here. Okay, I'm going to kind of probably work faster on this one as a whole. So number 9, this is example 5, make joint relative marginal frequencies. So I'm going to divide these 132 divided by 351 and 151 divided by 351 and 283 divided by 151. So this one, whoopsie, 351. 283 divided by 351. So first one is 0.376. Next one is 0.430. Next is the sum of those, 0.806. Okay, 39, 29, and 68 divided by 351. I'm getting 0.111, so it's just a 1 repeating. It must be exactly 1/9 of it, but 0.111, 0.083, and the sum of that is 0.194. There's kind of a round up there. That looks like it does add to 1, truly, so that's good. And then these ones, we're going to have to figure out what they are. So let's do 171 over 351 and 180 over 351. Also close to 50%. 48.7% for this one, so 0.487. And 0.513, 51.3%. There we go. There's number 9. Number 10. In a survey, 49 people received a flu vaccine before the flu season, and 63 people did not receive the flu vaccine. Of those who received the flu vaccine, 16 got the flu. Of those who did not receive, 17 got the flu. They're getting political. Make a two-way table that shows the joint and marginal relative frequencies. I'm going like, oh, they're going there. Interesting. All right, don't have the debate. For the record, I've never... Well, I'm going to stop talking. Do they want the relative ones as well? Both sets. So we need... Okay, let's do this. Flu... Oh, well, hold on. Vaccine. No vaccine. Flu. No flu. To be fair to this book, this was made pre-COVID. All right. 49 people received a flu vaccine before the flu season. So received vaccine 49. 63 did not receive. Now, the reason I'm writing this small right now is because they want the relative frequencies in a moment. I want to divide this by the total amount eventually, but I don't know the total yet. Oh, I can right now. 49 plus 63 is 112. Now, that would divide by 112, of course, and you get 1 in that case. But these will divide by 112 as well. So that's kind of where we're coming up with the numbers there. Now, they said... Of those who did not receive the vaccine, of those who did receive the flu vaccine, 16 got the flu. So 16 out of the 112 got the flu. 17 out of the 112 got the flu in this set. And we can come up with the rest. So we're going to do division, obviously, on those ones. We can even come up with some totals now. 16 plus 17 is 33. So 33 people in total got the flu out of 112, vaccine or not. And then here, no flu. 49 minus 16 is 33 in its own right. That's nice because I only need to do that division once. And then 63 minus 17 is 46. And I'll make sure that these seem to kind of add up to 1. 33 plus 46 is 79. So let's come up with those numbers as a whole. Excuse me. 16 divided by 112, 17 divided by 112, and 33 divided by 112 on the first column. We are getting, oh, that did not get 112 for this one. 17 divided by 112. So the first one is 0.143. Next one is 0.152. And the total is 0.295. I already got the 33 one. That's 0.295. So I'll do that again. 46 is 0.411. Looks like those will add to about 70.6%. So let's see. 79 divided by 112. 0.7053, so 70.5%. But this is an example of, why did I say 70.6? Because 5 plus 1 is 6. Mr. Robinson, 5 plus 1, you put 5 plus 1 is 5. Well, I divided the exact ones here. This plus this is going to give you 1, and that seems to line up. So I'm going based off the calculations there. 49 divided by 112. It's exactly 0.4375, but I'm going to still round that up. So 0.438. And then the other one must be 0.562. Let's see. 63 divided by 112. Whoops. 63 divided by 112. 0.5625. So 0.563 is the way that this one looks here. And then wait, that plus that is 1? No, it's just, these are just rounded versions. That's what you get for rounding. I mean, that's why fractions also have their place. Anyway. So I believe that those are accurate to the calculations. All right, number 11. So listen, this is taking a while. We're 45 plus minutes into it already, and we're only on number 11. A survey finds that 110 people ate breakfast and 30 people skipped breakfast. Of those who ate breakfast, 10 people felt tired. Of those who skipped breakfast, 10 people felt tired. Make a two-way table that shows the conditional relative frequencies based on the breakfast totals. I wonder if like drinking coffee constitutes as eating breakfast, is what I was going to say. Let me copy and paste the original kind of template that I made. Oh, I don't have it really anymore because I had it with this stuff here. Okay, I'll just paste one of those guys, then I'll erase all those things. I think that's easy to do. So just take this and erase, replace. Actually, that's what I did last time. Why don't I realize that? Okay, so ate breakfast. No, eat breakfast. And then tired. Wait. Yeah, tired, not tired. Okay. No, eats breakfast. 110 people ate breakfast. That's the total. This is conditional relative frequencies, by the way. So let's talk about that in a bit. Let's start with these. 110 total. 30 skipped breakfast. No, eats breakfast. That's a total of 140. 10 people felt tired from after eating breakfast. 10 people felt tired for those who skipped breakfast. 20 total there. And this would be 100, and this would be 20, and this would be 120, and those add to 140 as well. So that's the regular two-way table, right? Let's take that one and let's start doing conditional frequencies. They said based on the breakfast totals. So what they're saying is, and I'm trying to copy paste. It's like not, oh, I might be pasting right over it. Okay, so conditional relative frequencies is now doing, it's taking those numbers and it's saying based on the breakfast totals, not based on the tired totals, right? So here are the breakfast totals. The questions that could be asked, and they will be asked in future problems like this, I'm not specifically these problems, but just on the idea of these ones is, of those who ate breakfast, what's the probability that they were tired? Of those who ate breakfast. So we're dividing this out of 110 who ate breakfast, 110 here, and obviously this total is going to be 1 here. Honestly, this part's not going to matter when it comes to that aspect. The totals are going to be 100%, 100%, things like that. You could have them, but that's really not relevant. These totals can be relevant, I think. I'm trying to think suddenly if they are. Of those who did not eat breakfast, how many were tired, right? So out of 30 and out of 30. So we're going to divide those values. So 10, 10, 100, and 20. And then here is where I would probably, because you're not dividing by the same amount, here's where I might just use the decimal rounding version of things. Otherwise, I have to do a little bit more. I believe this number is 9.09%, 0.90909. Let's see. 10 divided by 110. Yeah, 0.09. 090909. So 09, excuse me, 0.091 when rounded. 10 over 30, we know that. That's 3 repeating. So 0.3 repeating, like that. This one, 0.909. Am I doing that right? I'm trying to do that one in my head. Yeah, 0.909, and this one should be 0.6 repeating. But I'm going to put a 7 there. So, no, yeah, I don't think these totals matter either. They don't really refer to anything. So when we're doing the conditional ones, it's just based on this set here. These totals are irrelevant. These should add to 1, and these should add to nothing of substance because they're comparing out of 2 different amounts out of these things. I should have realized that. Make a two-way table shows the conditional relative frequencies based on this. Yeah, so what we're saying is 9.1% of those who ate breakfast were tired. About 91% of those who ate breakfast were not tired. 67% of those who did not eat breakfast were tired. 33% of those who did not eat breakfast were tired. So you can compare now, even though this was 10 and 10, oh, you had the same amount of people that were tired whether or not you ate breakfast. Yeah, but there were a lot more people who ate breakfast, so that's a smaller percentage of those who were tired. So this is where you can now make a comparison. They're not asking you on this problem, but they will be. They'll ask you to interpret some things. And so that's kind of a version of the interpretation. Let's go to number 12. Use the survey results from exercise 10 to make a two-way table that shows conditional relative frequencies based on the flu vaccine totals. So let's look back at that one. Let's do a copy paste. Oh, it was right here. Number 10. Copy paste that one. And, again, here's the thing. First of all, the decimal values are rounded. Second of all, it's more numbers, I believe. I don't really want to use these ones when I don't have to. In other words, whatever 16, wait, hold on. What are we doing? Based on flu vaccine totals. So based on vaccine totals here and here. Now the totals are 49 and 63. You see, 33 divided by 49 is the same thing as, although it's rounded, 0.295 divided by 0.438. Would you rather do 33 divided by 49 or 0.295 divided by 0.38? Yeah, that's what I thought. So I'm going to finesse this a little bit. These totals will be, and remember, I can scrap these totals outright. Let me just kind of get rid of this part in whole, in its entirety. I can get rid of these. You just got to know these were 49 and 63. So 49 and 63 were here because we're going to be dividing by those two numbers. And then get new values here. So the vaccine totals, 49 and 63, are what we're going to divide. Of those who got a vaccine, what's the probability, or what's the percentage of those who got the flu? And of those who did not receive the vaccine, the 63, what's the percentage of those who got the flu? And then same thing here, 49 and 63. So those are the division values I'm going to be doing. Let's check them out. 16 over 49. 33 over 49. And those two numbers are 0.327 and 0.673. And then you have 17 over 63. And then 46 over 63. You, of course, can also do 1 minus that value. 0.270 and then 0.730. So 73% of those who did not receive the vaccine also didn't get the flu, things like that. Excuse me. Okay, let's jump to number 13 on problem solving. 3 different local hospitals in New York surveyed their patients. The survey asked whether the patient's physician communicated efficiently. The results given as joint relative frequencies are shown in the two-way table. I'm telling you guys, data collection, statistics are a huge real-world application. If you don't see the real-world application in these things on this is real-world stuff that, this data is collected all the time. So, okay. So here's the two-way table. What's the probability I'll leave the table there unless they ask me to make a new one, and it looks like they don't really. What's the probability a randomly selected patient located in Saratoga was satisfied with the communication of the physician? So we're only looking within Saratoga and want to look at whether they were satisfied or not. So what we want to do here, probability of satisfied, given that they live in Saratoga, is what we're doing. Now, all we have off this, all we have are the percentages, the decimals to work off of, so I can't give you the actual numbers. I could, maybe if I worked out sums, and I don't want to do that. So we're doing this one. A patient located in Saratoga. Don't worry about Glens Falls. Don't worry about Albany. We're just looking in Saratoga. Now, if they're satisfied, that's probability of Saratoga and satisfied, 0.288. Not all that were satisfied. Not 0.123 plus 0.28 plus 0.338. Divided by all that live in Saratoga. That's 0.288 plus 0.077. So I'll just go ahead and calculate that outright for you, because that percentage doesn't really matter to us unless we had to use it several times, and I don't think we're going to, but we'll see. 0.077, 0.288. Looks like I'm getting, I'm going to say it as a decimal, or as a percentage, 78.9%. So the question again, what's the probability a randomly selected patient located in Saratoga was satisfied? 78.9% probability that you will get a satisfied Saratogan. Part B. What's the probability a randomly selected patient who was not satisfied with the physician's communication is located in Glen Falls? Now we're looking within the row of the not satisfied. Hey, of you not satisfied people, yes, me, over here, Albany. Now we're only looking within here, so among that total, how many were located in Glens Falls? So for this one, it's probability that you live in Glens Falls, provided that you were a no. Not, I'll just put no. No. So that is 0.042 out of the sum of 0.042, 0.077, and 0.131. So out of that sum of those three. So that'll be, now by the way, when I do this in my calculator, I just did it for the last one, so I'm going to show you here. 0.042 divided by, I'm going to be using parentheses on this part in the sum. 0.042 plus 0.077 plus 0.131. So that'll give me that. And again, exactly 0.168, so 16.8%, not even approximated. But yeah, I'm going to write those ones as percentages. I think when they're asking for probability at this point, I want to do that. So 16.8% exactly, based on maybe those values were rounded to begin with, but we don't know that. Part C. Determine whether being satisfied with the communication of the physician and living in Saratoga are independent events. Now, this is where I might get a little, this is where I might mess up a little bit. Satisfied with the communication of the physician and living in Saratoga. So what you want to do is look at the probability, I should be fine, of satisfied and Saratoga. The probability of satisfied and Saratoga, that's just that number that you see there. That's the 0.288. We want to see now that if you are satisfied, that if you're a person who is satisfied, and then I believe this is what you're supposed to do. And then if you're a person who lives in Saratoga, and we multiply those two probabilities, we want to see if that's the same thing as this. That's what I believe we're supposed to do here. So now we want to see probability of satisfied. Now satisfied is the sum of 0.123, 0.288, and 0.338. So those add up to something. I'll get that in a second. I just want to write these things out so I have them. Probability of living in Saratoga, we actually already have that value. We saw that. Oh, I didn't actually add them though. 0.288 plus 0.077. So see, it did come in handy, and I didn't come up with the number. All right, let's figure out what those two numbers are. So 0.123, I'm just going to say 123. 123 plus 288 plus 338. It's 0.749. We're going to end up multiplying 0.749 with this other number. 0.365. We want to see, does 0.749 times 0.365 equal 0.288. That the probability of being of a satisfied person who lives in Saratoga is the same as taking those two events, probability of someone who's satisfied and probability of someone who lives in Saratoga. Those are two different questions, or are they? That's the question. So let's do 0.749 times 0.365, and I'm getting 0.273. So 0.273, that's not the same as 0.288. Close, but not close enough. I think we have to be rounded approximately to 3 decimal places to make that the same. So are these independent? No, these are not independent. I was trying to realize if I wanted to say, are these independent or dependent? These are not independent. Okay. All right. But anyway, dependent there. Number 14. Problem solving. A researcher surveys a random class sample of high school students in 7 states. The survey asks whether students plan to stay in their home state after graduation. The results given as joint relative frequencies are shown in the two-way table. So, same kinds of questions as before. How did I use this last time? I didn't make a table. I just used the ones they had there. So, part A, 14A. What is the probability a randomly selected student who lives in Nebraska plans to stay in his or her home after graduation? So we're looking at Nebraskans. So if they plan to, that's a yes. Doesn't seem like many will. Probability of yes given Nebraska. Yes given Nebraska. Okay. So that's 0.044 out of the sum of, so this is the sum, 0.444. Looks like that's a little less than a tenth, so or a little less than 10%. 0.44 over 0.444. Now, where am I getting 0.444 from? I'm adding those two up because that's all the Nebraskans. So 0.99. Did I say percentages before? 9.9%. 9.9%. Part B. What's the probability a randomly selected student who does not plan to stay in his or her home state after graduation lives in North Carolina? So does not plan on it and lives in North Carolina. So among the no's, what are those? So probability of North Carolina given no. So we're doing 0.193 out of, now I got to add these ones up, I don't know it. 0.4 plus 0.193 plus 0.256. All right. 0.193 divided by, let's see if I can use 0.4 plus. Oh, did I do something wrong there? 0.4 was what? Oh, I didn't put a decimal here. Hold on. I put a 0. All right, 0.227, so 22.7%. 22.7%. So again, going back to interpreting these things here, on part A, only 9.9% of Nebraskans will return home after graduation. Was it stay home after graduation? And then 22.7% of the no's are from North Carolina. Of those who will not stay are from North Carolina. Part C, probably a independent question. Determine whether planning to stay in their home state and living in Nebraska are independent events. So, what is the percentage of all Nebraskans? Probability that you have a Nebraskan. That'll be the 0.444 value. So 44.4% of all Nebraskans. Probability of staying home, yes, is adding up 0.044 with 0.051 with 0.056. That's the other states, by the way, which is 44 plus 56, 0.151. I think I did that correct in my head. We still got to do a calculation after. So probability of Nebraska times, I guess I'm writing this in a different order than I did before, times probability of yes. Let's see if that's the same as probability of Nebraska and yes. Let's see how those ones compare. So we have to do 0.444 times 0.151. I think that's how that adds up. I think so. And let's see if that's equal to, what's probability of Nebraska? And yes, that's 0.044. So 0.444 times 0.151. And that's 0.067. So 0.067 is not equal to 0.044. So like last time, this once again, not independent. Not independent. They'd be dependent if they were equal in that case. Okay. Couple non-independent folk. Error analysis in exercises 15 and 16. Describe and correct the error in finding the given conditional probability. So we have a two-way table set up. Excuse me. Let's find the probability that you respond to yes, given that you live in Tokyo. So they take the Tokyo and yes, 0.049, divided by the probability of people who live in Tokyo, 0.356. Well, this is not the probability of people who live in Tokyo. That's the wrong number. That's the probability of all yeses. They need to take this number, 0.39. So for number 15, they did not take the probability of all Tokyo citizens. They took the probability of all yeses. I never typed out yeses to see if it's a word, but it is, and I guess it makes sense that it is. So, probability of yes given Tokyo. Instead, they have the right wording for it, but they had the wrong numbers. So it is 0.049, but on bottom it's 0.39. 0.39. At least we know there is an error, so we know it's correct. Otherwise, I might look at it and go, oh yeah, it looks good. 0.39, and I get 0.126. And they're keeping it as a decimal, so I'll do the same. 12.6% though. Now that's number 15. Number 16. Probability of London and given no. London given no. So given no, we're looking at this set here. Probability of London. So we're going to divide this by this. They divided by probability of London. They selected the right probability for probability of London, but they weren't supposed to select probability of London. They were supposed to select probability of no. So when given no, they chose to divide out of the probability of Londoners instead of the probability of no responders, of no responses. So they should be dividing, so they had the wrong thing to state, so I want to kind of start that from scratch. Probability of London given no. Given no is out of all the no's. So on the bottom, that's probability of no. And on top, it's probability of no and London. London. No and London is 0.112. That was right. They divided by the wrong thing. They have to divide by 0.644. And we're getting 0.174. That one. Okay, let's go to number 17. You want to find the quickest route to school. You map out 3 routes. Before school, you randomly select a route and record whether you are late or are on time. The table shows your findings, assuming you leave at the same time each morning. Which route should you choose? Explain. So I'm going to copy and paste this one. Because listen, they tally it. I want to see them as numbers, if y'all don't mind. I know we can say them out loud, but just having the numbers, I think, will just be a preference as an overall. And then we can do more things with it. So I'm going to write the number, then I'll erase them afterwards. So the number here is 7, this is 11, and 12, and this is 4, 3, and 4. So let's get rid of these. And keep those. I mean, I get why they tally, because like that's the person doing it. They're going like, yeah. Oh, shoot. This might take a while because I have to keep these ones on top. Here, I'll just write it again. 7, 11, 12, and 4, 3, 4. Okay. Sorry about that. Technical. If you want to follow it, you have to get into technicalities. All right. Assuming you leave at the same time each morning, which route should you choose? So you don't necessarily just want to choose the one that has the most times that you were on time. You need to compare them to everything else. So routes A, B, and C have conditional kind of, comparisons here when you do it conditionally. Probability of on time given that you used route A, and on time given route B, and on time given route C. Those are the questions. So for A, you were on time 7 of 11 times. Part B, you were on time 11 of 14 times. Part C, you were on time 12 of 16 times. So 7 of 11, because you're adding those, right? Because the times that you were late. Notice that it's just conditional along the rows. So 7 over 11 is 0.636. 11 out of 14 is 0.786. And we should know that's 3/4, so that's 0.75. That's not even exact, that's not even approximate, that's exact. So that one's 0.75. So despite the fact that route C you were on time more times, you also took route C more times, and just barely, but route B seems to give you the best route that you should choose. You should choose route B. Now my explanation is in my numbers. This is the one you want to choose as the highest value. It's the highest frequency of being on time. Let's go to number 18. I think it's the same kind of question. Let's see which group should be awarded the teacher's prize. So here you have a teacher assessing 3 groups of students. I'm going to get the copy paste stuff ready. Over a period to offer one group a prize. Over a period of time, the teacher records whether the groups meet or exceed expectations on their assigned tasks. So exceeding is kind of the better one. So which one should they award the prize? Just based on overall percentage of those. How often a group does it in terms of frequency. So let's remember these numbers. Oh, let me write them here. 12, 8, and 9, and then 4, 5, and 6. So, I mean, you know what? Can you see the numbers for what they are? I think we're good. I think before I thought we were going to have trouble. So probability of exceeding, given that we're looking at group 1, and probability of exceeding given group 2, and probability of exceeding given group 3. That's what we're looking into. So here we'll do 12 out of 12 plus 4, 16. That's 0.75. In this one we'll do 8 out of that 13, yet to be determined. And here we'll do 9 out of 15. 9 out of 15 is 3/5. That's 0.6. It's not going to be that one. 8 out of 13 is 0.615. So group 1 not only exceeded expectations most of the time, but they also did most often. So that is a good reason to be choosing group 1. Group 1 should be awarded top prize. All right. Okay, cool. Let's move to number 19. Number 19, open-ended. Create and conduct a survey in your class. Organize the results in a two-way well, I can't do that here. In a two-way table. Then create a two-way table that shows the joint and marginal frequencies. I can't do that here. I mean, I can give you the idea of what you can do, and you can try it for yourself. You can do, hey, class, how many of you are male? How many of you are female? I mean, you also have non-binary stuff to do. How about how many of you are, you could break it up by grade. You can do upperclassmen and lowerclassmen, so you don't have to do 4 sets instead of freshman, sophomore, junior, senior. Maybe you're in 8th grade right now. But yeah, you can do upperclassmen, lowerclassmen. How many of you are an only child? Let's see. How many of you are taking a foreign language class? So we could do one that is. Let me get one of the things that we had before, like this one. Copy, paste. So we could say, oops. We could say upperclassmen, lowerclassmen. I mean, I guess the problem with that is you might have a whole set of like freshmen. Okay, here. You know what? The book did male, female. I'm going to do male, female. So male, female. I just don't want to exclude people. How many? I mean, you could do more sets. How many? I forgot what I said. Oh, a foreign language. Take a foreign language elective or whatever. Foreign lang. Or no foreign lang. Okay, and totals. So you can do it like that, and you'd come up with these values here, right? Well, you would, I mean, you have to kind of get some of that information out, but you need to come up with the males who take a foreign language. You can't just say, raise your hand if you're male, like, you know, like raise your hand if you're male, raise your hand if you're female. Okay, now everyone raise your hand if you're this and that for foreign language, not foreign language, because you're going to miss out on information. So you need to get more. Let me use Chat GPT. I'll have them come up with one for me. Create a made up class of 35 students, some male, some female, and tell me how many male students are taking a foreign language class and how many female students are. So I'm going to Chat GPT and I'm asking them that. You'll see the question after. My face is in the way there. Let's see. Oh, geez. Oh, my gosh. No. I don't know. I don't care about the names. Whoa. Okay, there we go. So, ooh, no. That's not what I want to say. Disregard names completely, please. Have some of them not be taking a foreign language class. Just don't tell me how many are not. Because I want to come up with that for myself. Not that you have to do that, but we can do that. No. But if this Chat GPT, if there are 35 students total, I want some of the 35 to not be taking a foreign language class. I'm going to restart them. Hold on. I'm going to go back to my initial thing. Okay, let's do this. I want a 35 student class, some male, split between males and females. Make up an amount for me. Sorry about this, guys. You can do this for yourself. What? Diversify a little bit more. Sure. Okay, 19 females, 16 males. Okay. That's right. It's good to have a diverse mix. Okay. Make a number of the 19 students who are taking a females who are taking a foreign language class. Don't have them all. Do the same for males. There we go. Okay, so here we go. that was an ordeal. Okay, so 16 males, 19 females. That's what I'm putting here. And then they said 10. I mean, I could have done this for myself, but I wanted this. 10 males are taking the foreign language, and 14 females are taking a foreign language class. All right, now let's complete it. Right? That's 35 students total. That's 24 total that are taking foreign language. 35 minus 24 is 11. 19 minus 14 is 5. 16 minus 10 is 6. Is that all they needed? They needed the joint marginal frequencies, that's it. Not the relative ones, and that's it. So that was a longer problem than needed to be because ChatGPT and because I didn't have an actual class, but I had ChatGPT give me a class. Thank you, ChatGPT. All right, number 20. How do you see it? A research group surveys parents and coaches of high school students about whether competitive sports are important in school. Yes. The 2A table shows the results of the survey. Yes. All right, part A. How do we see it? What does 120 represent? Let's type these. 120 represents the number of no responses from parents. Part B, I'll put the B and C in a second. What does 1336 represent? 1336 represents the total number of yes responses. It's also the marginal frequency for that. And then part C, what does 1501 represent? 1501 represents the total number of people surveyed. Okay, so that was part B and C. Let's make sure to put those ones in. So that is how I see it. Do you see it that way? I do. Okay, number 21. Number 21, making an argument. Your friend uses the table below to determine which workout routine is the best. Your friend decides that routine B is the best option because it has the fewest tally marks in the does not reach goal column. Is your friend correct? Explain your reasoning. Well, not necessarily, because what if they never reach their goal in B? It's all about the conditional relative frequencies. So your friend still may be correct, but that's not a good reason. Hold on. Let's compute them first. So let's do probability of goal reached given group. Goal reached given routine A, probability of goal given B, and goal given C. I'm going to do it based on goal. I could do not goal, but then I'm coming up with the lowest number, and I just don't want to kind of look at it that way. So first one is 5 out of 8. Next one is 4 out of 6. And last one is 7 out of 11. I think I could tell you these numbers. This one I might have trouble with. Wait, was this the 0.636? 0.636 for this. This is 0.667. And this is 0.625. B still wins, but it's for a different reason. So your friend is correct, but for a different reason. You need to compare the conditional relative frequencies as it matters how often they do or do not reach their goal. And B still, routine B, wins in that department. Come on, type. Okay. All right, there's number 21. Okay, number 22, modeling with mathematics. A survey asks students whether they prefer math class or science class. Of the 150, whoa, white, green. Of the 150 male students surveyed, 62% prefer math class over science class. Of the female students surveyed, 74% prefer math. Construct a two-way table to show the number of students in each category if 350 students were surveyed. So the thing about this one, and I don't know if the last time I copied and pasted, but I'm going to take this here because I think I can use it. With this one here, when you can take percentages of numbers by multiplying the decimal equivalent by that number. After all, that's where percentages have come from for us. They were decimal equivalents. So I can still do male and female in this set, and we'll talk about math versus science. These are preferences. Math versus science. Now, The male portion, there are 150 male students surveyed. There are 350 total students surveyed. That means there were 200 female students who were surveyed, so we can work that out. 62% prefer math over science. Now that means 0.62 is going to be multiplied by the 150. That's how we come up with that number. I'm going to erase that in a moment. But 0.62 times 150 gets you 62% of 150. Because it says 62% of the male students. It doesn't say 62% of everybody. Now that number is 93, and it's 93 exactly. Based on that, I can figure out how many preferred science. You could also take 38% of 150, but 150 minus 93 is going to be 57. So there's that. Female of the female students, 74% prefer math. So I like that math is preferred over science for there. That's good on the math book to actually show some bias, which is nice. 74% of 200. Now we should also know 74% of 200 is 148. So that's 148, and then in this case here, that would be 52. Now we can come up with these totals. This would be 109, and that total there is 241, I think. And 241 plus 109 is 350. Okay, that would be number 22 with that. You multiply the percentages by those things. Notice they used a conditional relative frequency of the male students, 62%, of the female students, 74%, not of the whole amount. All right, number 23. Use the Venn diagram to construct a two-way table, then use your table to answer the questions. So in this Venn diagram, we see we have exclusive dog owners, exclusive cat owners, owners of both dogs and cats, 92 of which do not own any of them. And let's go from that. So that's owns a... I need to think about what the two-way table portion of this thing is. Is it owns a pet versus not owns a pet? And then among those who do not own a pet, oh, let's see, that doesn't work. Two-way table. Owns a dog. Duh. I was trying to think of, okay, timeout. I was very slow to the punch on that. Let's do this. I'm very sorry, guys. I was thinking of putting dog owners and cat owners in the same category together, but that's the thing. They're supposed to be in different categories. So, what are we going to do? Owns a dog, doesn't own a dog. Owns a cat, doesn't own a cat. Hello? So, owns dog. Dogs rule. No. Own dog. And owns cat. And no own cat. Let's see if the world is right in what we should be doing here. If you own both a dog and a cat, that's 36 of y'all. If you're an exclusive dog owner, that means you don't own a cat, that's 57 of y'all. 25 own a cat but do not own a dog. And 92 own neither. Now we can come up with the rest. Construct two ways. So 36 plus 25 is 61. 57 plus 92 is 149. 36 plus 57 is 93. 25 plus 92 is 117. 93 plus 117 is 200. 61 plus 149 is not 200, so I did something wrong. That is this one. This is 210. 93 plus 117 is 210, and that's why we double check that. Okay, are we right in the world? There are 93 who own a dog and 61 who own a cat. I'll take it. 93 or 57 own a dog only without a cat, and those who own a cat, let's see, I don't know. I'm trying to interpret it later. Maybe they'll ask us questions. I'm just trying to make sure there are more dog owners in the world. All right, part A. What's the probability a randomly selected person does not own either pet? So, randomly selected. There are 92 who do not own either pet. Probability of no cat or dog. That's going to be the 92 out of 210. So that's what you would do in that division as well, and just in general if you did the relative frequencies. And that's going to be 43.8%. So almost half of them own neither. That probably seems pretty commonplace. Part B. What's the probability a randomly selected person who owns a dog also owns a cat? So among the dog owners, how many do own a cat? So now we're going to take probability of cat given dog. That's owning. So we're going to take 36 of those out of the 93. It's going to be close to more than 40%, I believe, as well. So 36 out of 93. Oh, never mind. 38.7%. Okay. That's part B. Okay, number 24. Compare two-way tables and Venn diagrams, then describe the advantages and disadvantages of each. They're both visual, but Venn diagrams have a little more of a visual aspect to them. Venn diagrams provide a visual sense that immediately hits viewers, like statisticians, whereas two-way tables require more overall interpretation. I'd say that, however, two-way tables have the ability to show totals, to show totals at the same time. And honestly, with more than two categories, with more than two items in a category, or categories, I should say, it is less confusing than Venn diagrams. Once you get this, that's a personal opinion. Once you get a Venn diagram that has like a third circle, now you're getting into this territory where, okay, now here are the, bird owners or whatever. Now you have to look at a bunch of numbers within that. You're really trying to look at that overlap portion that can get really confusing because, boom, that's potentially, that's argued as to whether that's true or not. But as you just keep increasing it, right? What about now you talk about, hamster owners and stuff. That deep overlap within here can become quite the mess, I think. And so I think that at some point it kind of gives up. Whereas here, it's just more rows and columns. You still can look down the list and see what's going on with them. And I think that's okay. So it's just kind of one versus the other there. So there are advantages and disadvantages to both. Okay, number 25. I have two more questions. Number 25. A company creates a new snack, N, okay, and test it against its current leader, L. Oh, N for new. L for leader. The table shows the results. Current L consumer prefers L. 72 prefer L and 46 prefer N. Not a current L consumer, 52. Okay, I gotcha. The company is deciding whether it should try to improve the snack before marketing it, and to whom the snack should be marketed. The new snack? Wait, the company's deciding whether to try to improve the snack for, probably the new snack. Use probability to explain the decisions the company should make when the total size of the snacks market is expected to change very little and expand very rapidly. What? I'm going to start with the probability portion. Use probability to explain the decisions the company should make when the total size snacks market to change very little. I guess they're saying that if you don't kind of go to the new or what have you, then how does that thing compare kind of as a whole? So we probably want to look at conditional probabilities in that sense, and we want to look more in terms of, let me copy paste that. We probably want to look more in terms of like, given that you are a, let's see, I'm trying to figure out which givens we should use. Given that you prefer L, explain the decisions the company should make when the total size of the snacks market is expected to change very little. When it's expected to change very little, and I'm going to do probabilities last because I want to talk about which probabilities I'm going to use. When it talks about changing very little, I want to start marketing toward these folks here, the not current L consumers, because there's a smaller percentage of those who prefer N, and I really want to stick to the leader that's right now. So if it's not going to change very much in the snacks market, and they're not going to introduce more new ones, I really want to cater to them. So I'll talk about the probabilities, but this might be, 30% of not current L consumers. I really want to market them so I can hit them. Whereas I guess I'll stick with them as well. It really seems like we should change markets though. If it expands very rapidly, I feel like I should be hitting. I wonder if there's a reason I should be looking at this. The current ones, I suppose. I suppose it's just about whether you're doing the current ones or the not current ones, and then that's the ones that you should be hitting. That's kind of how I'm looking at it. Let me think about it. These are the kinds I have to think about with what they're saying. Okay, so I feel I kind of misread the problem. I thought they were talking about how they should talk about the marketing and who they should be marketing. They were talking about whether they should try and improve the snack before marketing. So they're talking about should they try and improve the snack. So use probability to explain the decisions the company should make on how much they should improve the snack before marketing if the market is expected to change very little. And to me, what that sounds like is if you're already a consumer and that's not going to change very much. So it's about keeping the things as they are with current consumers. So if because you're going to introduce this new snack. You're going to introduce it. So what you want to do is if it's not going to change very much as far as, people and stuff, you really want to hit these guys because they prefer the old snack. They prefer the leader over the new one. So you really want to improve the snack to get them to get them to jump on board. Not current consumers, if the market doesn't change, not current consumers of this one already prefer the new snack. So, and that's stuff that we have to do with probabilities. So when I look at this one, I want to look at the probability. This is part A. I want to look at the probability of that you prefer L given that you are a current L consumer. And that's 72 over 72 plus 46, which is 116, which is, it's more than 50%, right? But they said use probabilities. So 72 over 116 is 62% about. So 62.1%. So when there are more current leader consumers who prefer that snack, you really want to improve the snack beforehand. Because the current market, little changing market, has current, I'm using current twice. L consumers prefer L over N. You want to improve the snack before marketing it to sway them over, right? They don't prefer the new one, so you need to improve it before marketing again. Now, part B says if it changes rapidly, if it expands very rapidly. So, you hit more of these folks here, right? Expands very rapidly. So when it comes to preference, there are more people who weren't current consumers that are expanding there that do prefer it over those who prefer it there. So among those who prefer it, those are not current L consumers. So there's no need to improve it because those are the ones who already like it anyway. So probability of prefer new, of current, not current L, given that they prefer new, is 114 over 114 over that plus 46, 160, which is about 0.7125, so 71.25%. You already have the market if it expands rapidly. If the market expands rapidly, you already have a great deal of non-current L current L consumers, did they say consumers? Consumers who prefer N. So there is no real need to improve the stack. You already have them if they are expanding. So that's the idea of it to me. That's what I'm going to go with on that one. Okay, I got one more question, and that final question on number 26. The time did not ever improve for me when it came to these videos. But number 26, Bayes' theorem is given by that. P of A given B. I remember the name. I don't remember how it kind of works. Probability B given A times probability of A over probability of B. I could probably think of like an example of like how I would use that, but use a two-way table to write an example. Oh, I have to do that. Use a two-way table to write an example of Bayes' theorem. Can we use any of the old ones? Let's use the one we made up. Let's do the foreign language one. Where is that? That's math science. Here it is. So the foreign language one. Let's see if this works. Let's call male. Wait. Let's call this category A and category B. Let's do probability of male given that you take a foreign language. Okay, probability of male given you foreign language. So that means you got to swap that. Probability of foreign language given male. Oh, actually, let's start with this. Probability you're male given you take a foreign language. That's 10 out of 24. That's 10 out of 24, which is, I'll keep it as a fraction for now. That's 5 out of 12. So 5 out of 12. Let's see if that equals probability of foreign language given male, times probability of male, probability of A, divided by probability of, I guess, foreign language. Okay, so 5/12 equals probability of foreign language given you're a male. That is, given you're a male, that's 10 out of 16. So we'll do 10 out of 16 times probability of male. That's straight up. Male is 16 out of 35. 16 out of 35 divided by probability you take a foreign language. That's 24 out of 35. 24 out of 35. Now, if I'm going to do some, I'm going to keep the 5/12 on this side as it was. 5/12 equals. Over here, dividing by a fraction is multiplying by its reciprocal, and I'm going to reduce any fractions that I have as well. So 10/16 reduces to 5/8. I want to see where these numbers come from. Times, I don't think that reduces, and that's fine. Times, and I'm going to flip-flop this, 35 over 24. So the 35s here cancel. Oh, you know what? These 16s would have canceled as well. Let me keep that 10 out of 6. Let me keep this as 10 out of 16 and cancel the 16s. 10 out of 16. These 16s cancel. You're left with 10 out of 24. Remember, this 5/12 was 10 out of 24 as well. So let's keep that as 10 out of 24, just to 10 out of 24, 10 out of 24, 10 out of 24. And you can see now that we get 10 out of 24 equals 10 out of 24, and that checks out. Obviously, they can be rewritten as 5/12 as well. We can get the decimal, we can get the percentage, but it seems to clear out. I don't know like why it works. I mean, I can see that it did, and certain things cancel when you get there. So it's all good. It seemed to show that it works. I don't know, but there's an example of Bayes' theorem. Guess I'd have to look more up on it. All right, guys, and that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. I know that the statistics stuff can be very conversation heavy. You can write a lot of things and use a lot of stuff with the calculator. It's as it goes. Coming up next after this would be the 5.1 to 5.3 quiz review, if you will. So everything from the sample spaces and probability, where we probably have to list a lot of things out, to independent and dependent events, to and conditional probabilities, to now whatever we were just talking about, two-way tables and probability. So guys, that'll do it for this one. This is Mr. Robinson. Thank you so much. Take care, and I will see you in the next one.